All right, so this problem says in 1986, an enormous iceberg broke away from the Ross Ice Shelf in Antarctica. It was an approximately rectangular prism, 160 kilometers long by 40 kilometers wide and 250 meters thick. What is the mass of this iceberg given that the density of ice is 917 kg per meter cube? How much heat transfer is needed to melt it? How many years would it take sunlight alone to melt ice this thick if the ice absorbs an average of 10 watt per meter square? Um, 12 hours per day. Okay, so so let's draw this shelf. And of course, this drawing is not to scale. Okay, so 160 kilometers is roughly as wide as Florida. Okay, so imagine this. So here's the shelf. Here's Florida. This is the ice shelf. This is Daytona Beach. This is Palm Coast, if you guys know Palm Coast. That's the ice shelf. 250 meters is about 5 times as high as the tallest building in Daytona Beach. You can go to the beach and. Okay. All right, so what is the mass of this iceberg? Density is mass divided by volume, so mass is density times volume. 917 kg per meter cube, and the volume is 160 kilometers, which is that many meters, times 40 into 250 meter cube. Okay, so again, in this business, it's good to take care of powers of 10. We'll call this 9.17 times 10 to the 2, 2, 4, 7, 10, 11, 13. Okay, so that's 10 to the power 13 kgs times so the mass of this ice shelf is 1.5 times 10 to the 15 kgs. Okay, so here's a way to think about it. 1.5, 1500 kgs. 1.5 times 10 to the 3 kgs is the mass of a car. So the mass of a trillion cars. Yeah. That's how much this thing weighs. How much heat transfer in joules is needed to melt it? Okay. So now when you're melting ice, what are you doing? It's a phase transition and the heat is latent heat. Okay. So Q is the mass of the height of the ice times the latent heat of fusion of ice. That's how much heat you need. And what is the latent heat of fusion?
334 joules.
334. Okay, so if you want to melt this much ice, you need 5 times 10 to the 20 joules. Okay, and where are you going to get this heat from? Well, I mean, in this problem, the ice shelf melts and goes into the water. The water temperature is above 0 degrees, and that you would get heat from there too. But what we're going to do is we are going to melt it just from sunlight. And they tell you if the ice absorbs 100 watt per meter square of sunlight, okay, about 700 watts per meter square is falling, between 500 and 700. So the ice is not absorbing all of the sunlight that's falling on it. Why is it not absorbing all of it? I'm sorry? That's right. Okay. So if it was dark snow, then it would absorb more heat and it would melt faster. Okay. It's a good thing. It's reflecting stuff. Okay. So how many years it takes sunlight alone to melt ice this thick if the ice absorbs an average of 100 watts per meter square? Okay. See, the amount of heat is the rate at which heat is falling times the area times the time. Okay. So this is 100. This is 100 watt per meter square. So and that'll be the areas, the top area of the ice shelf. That's the area that's exposed to the sunlight times the time. Okay. All right. So the time it would take to absorb that much heat would be that 4.91 into 10 to the 20 joules. That's how much heat you have to absorb. The rate at which you're absorbing is 100 watts per meter square, joules per second per meter square. And the area of the shelf, it's this area that's relevant. Okay, so 160 kilometers by 40 kilometers. Okay. And so you see joules will cancel and meter square will cancel, and you'll get the time in seconds. So, and then we'll convert that to years. So, but let's take care of powers of 10. This is 20, minus 2 is 18, and you have 6, 7, 9. So 18 minus 9 is 9. Okay, so this is equal to 4.91 divided by 1.6 into 4 into 10 to the 9 seconds. And this works out too. Okay, so let's convert that to years. And 1 year is 365 days. Each day has only 12 hours of sunshine. Okay. Okay, so so it'll take sunlight 50 years to melt this shelf, block of ice. Okay. All right, do you guys have any questions on this? All right.